So my name is JD. I'm a senior product manager in Google. And with me is John Banning, who's a staff software engineer and the technical lead for the Stackdriver Query Notation, which we're very excited to introduce to you today. So we're going to be talking about how to incrementally build powerful queries with the Stackdriver Query Notation, and also how that gives you more flexibility and power to increase the observability of your applications and your infrastructure, whatever you're using in Google Cloud and beyond. But before we get going, I'd love to know a little bit more about everybody here in the audience. So let's see some hands. So who here is a developer? All right. What about an operator or SRE? Oh, wow. And both? Truly, DevOps? We're doing everything? Yes, a few? OK, cool. Anybody who's a language geek? Wow, a few. Awesome. OK, so hopefully we'll have several things for each and one of you. But this is an intermediate level talk. We're going to go into the nitty-gritty details of query language that John essentially designed and worked with the team. But as I said, we're hopefully going to show you through demos and other things how we get there. So here's the plan. We'll start with a brief overview of observability within Stackdriver, and particularly with the query notation, and introduce you to query notation itself. Then we'll jump straight into details from the beginning. And we're going to see a lot of shorter demos and showing how you can actually use this language to create this very robust, powerful queries. So John will spend a few minutes talking about how a basic query is formed, and then he's going to build up on that to create more queries. And then we'll get even into some demos of advanced queries, then to come back to the end, recap, and then give you some call to action so you can actually get access to query notation, use it, and of course, please give us feedback. So let's jump right in. So of course, in the end, we do have time for questions. We're going to leave a few minutes. So I'm sure there's microphones up here in the front, which you can use. And if we run out of time, we're, of course, going to be also outside for you can come and talk to us as well. So let's go right into the piece of observability. So whether you're a developer or an operator or SRE, or you're doing both, or you're just doing analysis and so on, there's always that time when we all wish we had just a little more observability. Maybe because you're dealing with an incident in your application, and then your users are not able to access their carts and their checkout services. Or maybe because you're doing proactive monitoring, and you're really trying to do analysis on some specific state of your application or infrastructure. Or maybe because you want to control a little bit of time, and you want to do demand forecasting. You want to look at how your retail application is doing now, the demand is getting, compared to last season of Black Friday, for instance. Now, in those cases, you really want to be able to go and inspect your systems, your applications in detail. Now, many of observability tools allow you to do this in some ways, very much in the same way the Stackdriver does. And we're going to offer you another more powerful and flexible means to do this. So this is precisely the whole idea of being able to increase and get observability for your cloud applications is what Stackdriver is meant to do. Stackdriver is a product suite that offers a comprehensive set of tools that together provide very rich observability of your cloud environment, your cloud services, your application, and so forth. And so the idea that we're trying to do in many of the services, and today we're going to focus primarily on the monitoring side. We're going to focus on metrics and time series. But the idea here is that we want to take the toil of doing ops management away from you as much as possible. Those things that really are hard to do, or easily automatable, and so forth. We want to help you take advantage of those so that you can focus on what matters most, which is your business and your application. And so to that end, we've built an enormous machinery. It's a set of systems that we use internally at Google to also how we monitor and get observability for many of our own products. And so these systems bring together a lot of different things. Built-in metrics, built-in metrics and logs, as well as snapshots and traces. And we put all of those together. They're coming from cloud services. They're coming from open source components. They're coming from cloud native infrastructure, even from other cloud providers. And we aggregate, put those together to help create and infer relationships between resources, to understand and evaluate alerting policies, to alert you when a symptom of perhaps the prediction of a failure may come in. And we give you powerful visualization tools to do all of this. So that always with the intent of making ops easy for you and increase that observability. So again, if we focus on the monitoring piece, if we focus on metrics and time series, Stackdriver monitoring, of course, allows you to do this today. You can inspect on demand in Stackdriver monitoring using the Metrics Explorer. Anybody here has used a Metrics Explorer before? A few of you? Oh, wow, several of you. Great. So for instance, you can look at the CPU request utilization metric for those Kubernetes container resources. You can filter them by the namespace that is, let's say, the default namespace that has my application at this moment. And I can group them by container name and by a location. I can certainly do that with a metric and get that on-demand type of visibility. But what if I want to do something different? What if this may not be enough, and we know that. Sometimes you want to slice and dice your time series data and your metrics in a way that is just convenient to you. And maybe you want to do composite metrics. Maybe you want to do arbitrary math functions. You want to control time and so forth. So this is exactly what we're doing today by introducing the Stackdriver Query Notation. Stackdriver Query Notation is a flexible and comprehensive language that allows you to do precisely that. It allows you to build powerful query metrics so you can inspect on demand, so that you can analyze the state of your application and infrastructure, and so that you can build robust dashboards, so you can do proactive monitoring, or also so you can do alerting, and then, in general, increase the overall observability of your cloud workloads. Now, the Stackdriver Query Notation is built on a consistent data model, so it provides a very solid foundation for all your query buildups. It is also based on a popular pipeline idiom, so it's easier to incrementally build and debug those queries that you have. And it also offers powerful operators for you, so to do precisely the sort of things that I mentioned: composite queries, queries of composite functions, arbitrary math, ratios, time shifting, and so on, which John is precisely going to show us in a few minutes. So just to get a sense of how this works, let's do, this is a Metrics Explorer. And we have already here a standard query set up, the one that we just mentioned in the previous slide. And what you can do is you can click on Query Editor. And that should give you directly now the equivalent of that essentially query that you have now in query notation. So notice what you have here. It's already grouped by window, by main, and I have another group by container name, location, and so on. And I immediately get the same time series that I would get otherwise. Now if this was all too fast, don't worry, because this is exactly what we're going to be doing next. Jonathan's going to take us into the details of how to start from a query like this and build up on that and show us several advanced queries as well to really get you into how you can increase observability of your apps. So I'm going to hand it off to John, who can start on some of this journey.
All right, I think we go back to the slides now. And here we go. We're going to go through the query notation in 7 steps. I'm not going to read these to you because we're going to start right in. So basic query. The most basic query, every query in the query notation starts with a fetch operation. The fetch operation, we see one here, starts with the name of the operation, fetch, and one argument, which is the name of a table. When it evaluates, it's going to find that table in the database and return it or produce it as its output. Now you might be saying, wait a minute, we have metrics, we have time series. What's this table thing, and what's a table name? So let's look at that for a minute. Out in the cloud, we've got resources that we want to keep an eye on. Here's a Kubernetes node. And every kind of resource has associated with it a monitored resource type, in this case, K8s node. And the monitored resource type gives us a way to name that resource. And it does so by giving us a set of labels. And every resource of that kind will have a value for each of those labels. The project ID that owns the resource, the location where the resource resides or is being monitored from, and the cluster name and node name that were given when that Kubernetes node was created. And the monitored resource type and the value of those labels uniquely identify every Kubernetes node in the system. Now, now we're going to have a number of metrics on each one of these nodes that we're going to be monitoring. And each metric has a metric type. Here is a metric type for allocatable utilization on a node, the fraction of memory we could allocate that we're actually using. And the metric type gives the type of value that the metric is producing, in this case, double gauge. Gauge means that it's a state of the system that we can observe and that we'll sample to gather data from, being the amount of memory in use at that time. The other kind of stream that we see typically is a delta stream, where each point is the sum of some value, like the number of queries I've received or the number of CPU seconds I've used over some specific time period. Now, the other thing that might come with a metric type are some labels. This one comes with one label called the memory type, which can be either evictable or non-evictable. So there are two kinds of memory, and we'll basically have two instances of this metric with different values for that label to track the utilization of both of those kinds of memory. Now, these two things together uniquely identify a stream of data that we might be interested in collecting, and we put them together in what's called a time series identifier. The name of that time series identifier includes both the resource name and the metric name, has all of the labels from both the resource and the metric, and this uniquely identifies a stream of data that's coming in from the cloud to Stackdriver to be recorded. Now that we have a name for a time series, we can start collecting a time series. So a time series has an identifier that uniquely identifies it and a history. So we get the history consists of values that we've observed the metric to have and the timestamp when the observation was made. Now, obviously, we have a lot of nodes out in the cloud, and they have a lot of metrics, and so we're going to have a lot of these time series. And you might think of this slide as being reproduced once for each resource and metric type, and they'll have different labels, but the same time series identifier uniquely identifying the time series and a history associated with it. Now, in order to make these time series accessible to queries, we gather them together in a time series table. This is a relational, straightforward relational table. It has columns, one column for each of the time series identifier labels, a timestamp column. Oops, sorry, there we go. I went way too far. All right. A timestamp column and a value column. So every row in this table represents one observation, and that observation's time is here and value there, and the time series it's part of is identified by these columns. So you can think of this as containing all of the time series that involve a K8 Kubernetes node and this particular metric. And so that's what the name of this table is given by the resource name and the metric name. And so that is what the fetch operation names and the kind of table that it's going to return. All right. Now let's start building queries from that base. We build queries with a pipe operator. That's the method by which parts of queries are composed. Here, the pipe operator that connects different operations. Here we have the fetch operation we saw before connected by the pipe operator to a filter operation that we've added. And the way this works is the fetch operation produces a table. It's piped by the pipe operator to be the input to the filter operation, which transforms that table in some way and produces it as output, which is then the output of this query. So we can sort of see this in this diagram. There's the fetch operation. It's producing a table that's input to the filter operation, which transforms it in some way and produces another table as output. Well, what is the fetch operation, filter operation doing? Pretty straightforward. It's got one argument, which is a Boolean expression that's a predicate. And we'll evaluate that expression on every row in the input table. And those rows for which the expression is true, we'll keep, and those for which it's false, we'll drop. This is a fairly simple expression. It's basically looking at one column, the value of one column in the row, and asking, does it start with the word heapster? If it does, that'll be true. Otherwise, it'll be false. We'll see more complex expressions in a little bit. So basically, we're looking at the container column and all of the rows in the table. We're evaluating the predicate on them. We see the rows that have the predicate returning true. We throw away all the rows where it returns false. And this is the output of the filter operation. So this is a way to look at some specific subset of the data that you want, that you have in your table. Another thing you might want to do is to get a statistics about all of the things in the table. And that's done by the group by operation. So here we're piping the output of the fetch into a group by, which has two arguments. The first is a map expression, which is going to tell us how to construct the time series identifier columns in the output table. And here they're constructed by just taking the cluster name field from the input table stream ID, and that will be the stream ID of the output. And then the other part is the aggregation. I apologize. I'm pushing the wrong buttons here. The aggregation expression, which tells how to combine the value columns of rows that are mapped to the same place by this. So let's look at that in a little more detail. Here we're showing one stream out of the table. We have all of the stream ID identifier column values here, and each row is represented by a point in the table with its timestamp. And basically what the map does is basically transform this into this. And this is now the time series of the identifier. The history remains unchanged. Now, if we do that, we're going to have a lot of time series in the table with the same time series identifier. But we only want one time series in the output with that identifier. So basically what we're going to do is to apply the aggregator to these. We take all of the points at some particular time, and we apply the mean aggregator to them, getting the average value. And that goes into a point in the output table with the same timestamp and the mean value. And we keep doing that at each timestamp until we get to the end of the table, at which point now we have one output time series for the output table. And we do this for every value of cluster name. So for every value of cluster name, there'll be another group of time series like this, and we do the same thing, and that's how we produce the output table. All right, so let's look at that a little bit in action. Okay, we start with the basic fetch. We can see there's quite a few time series up on the screen here. And every line on this screen represents one time series in the table that was fetched by that fetch. Now we can add a filter to this. And what are we going to do here? We're going to look at the namespace name. We're going to look at the default namespace. And that's going to cut down the rows that we have, the time series that we have, to a certain smaller number of them. And we're also going to look at, we can add further predicates to that. So we're going to only look, some of these are running on-prem. We're only going to look at the on-prem ones. All right. And once we've done that, now we can look at a group by. And this group by is throwing away all of the time series identifiers. So there's only one stream in the output, and it has the default aggregator, which is to sum. But we can replace that aggregator with an explicit one. We could say mean, or we could say standard deviation. There's a very large number of aggregators we could use. But besides giving a single aggregation function, we can make an expression. We could, for instance, divide the standard deviation by the mean to get the coefficient of variation. And that's what we have. So this is over all of the containers in our application. Now, the next thing we can do is go to the map expression. And here we're going to put in this regular expression extraction that extracts the first component in the name of the in the pod name of our container, everything up to the first dash. And so this gives us aggregated information about each kind of container that we are running. All right. Now, after I've gone to all this trouble to make a query, I might want to save it. Well, you can do that. There we go. You can save it. You give it a name. And you can save it to a dashboard. You could create a new one, or we're going to use an existing one. And we save it. I think we save it. Does it not want to save itself?
Yeah, it's saving.
All right.
Let me just
We're going to try that again.
It's the last day, John. The demo gods are...
They are frowning on us. All right.
All right. We'll get to this.
You're going to have to trust us. You really can do this. And we would have gone to look at the chart on the dashboard and shown that you could edit the chart again. In fact, we could go to the dashboard and just edit some other chart just to show that it is, in fact, useful thing. So this is also a way of obviously, of creating dashboards. All right, here's one we saved earlier today, just to prove that we can do it. And you go back and you get a very similar editor view of that. All right, so let's go back now to the presentation. And so this is just for the record, the group by that we built before with a little bit more here. We've got an extra field that we added to the mapping, but this is pretty much the same thing. Now let's see, look at some more advanced queries from this. This is the base kind of queries that we've got. So here we go. We're now up to 0.5 in our 7 points. And one of the things that you might want to do is to look at outliers. That's always a lot of fun, particularly if your aggregation says, well, there's something wrong. Maybe you want to see if there's something wrong with specific things. So for that, you can use the top operation. It has 2 arguments. The first says, how many things do you want to see out of the collection of all the things? And the second says, here's how to select them. So this is an aggregation function. Max is an aggregation function. It's applied to all of the points in a time series to get the maximum value of that time series. And then we look for the time series with the top 5 time series for that value. You can use any kind of aggregator here. Mean is also a good one to use. And you can also use bottom here to look for things with the smallest amount. Another thing that you often will want to do is to look at more than one query at a time. So far, we've just been looking at one query. Here, we, in order to do that, you use these squiggly brackets and join. Between the squiggly brackets, you have multiple queries. Here, the queries are very simple, just a fetch operation, but they could be general queries put together by pipes, separated by semicolons. So this basically produces 2 different tables, one for each of the queries. Those 2 tables then are piped into the join, which combines them into one table, but that table now has 2 value columns, one from each of the input tables. And that can be piped into a div operation, which takes the 2 values, divides them, and produces a single ratio and a single value column table for output. So let's look at that in a little more detail. So here's how tables are piped through the join operation. Each of the 2 queries produces a table. Those 2 tables are independently input into the join, which combines the 2 tables into one table with 2 value columns. The div takes that table with 2 value columns, divides the values in the value column to produce a table with 1 value column. So how does the join do that? Transformation from 2 tables to 1. Basically, it's 2 steps. The first step, you're looking at every pair of rows, one from each of the 2 tables, and asking, do they match up in the time series identifier fields and the timestamp field? And when they find a pair that does, we say we have a match, and we're going to combine those two input rows into a row in the output table. And that's done basically by taking the time series identifier columns and the timestamp column, which are the same in both of those tables, and those become the column values for that row in the output, and then taking the value column from one table and the value column from the other, and those become two value columns in the table. And this is basically your straightforward relational database natural join. Okay, now here we just did something very simple with that table with two values in it. We just divided the two values. But maybe you want to do something a little more complex. Here we're fetching the received bytes and sent bytes for a pod. And we've joined that. So now every row in the table has the number of received bytes and the sent bytes. And we want the number of received bytes as a percent of the total. So that's this fairly straightforward expression. Val 0 is the first value in the table, which is the received bytes. Val of 1 is the second value. We could have used received byte count and sent byte count here. It wouldn't have fit on the slide as well, but it would be maybe more readable in some sense. We could have done that. So that's the sum of bytes sent and received. Here's the bytes received times 100, and dividing, we get the percent of those. So the value table operation basically allows us to do arbitrary computations on the input table. The join can handle multiple queries in it, and we'll join them all together. So you can look at more than two metrics at the same time. And you can create more than one value column on the output. Unfortunately, at this time, the Metrics Explorer will only display the first value in the column, but you might have additional computations that could use multiple values in the row, and the value operation will be quite happy to do that for you. All right, more demoing. All right.
Before we get, we actually had some latency, which is what we see here.
Oh, okay. Are we going to save the chart?
It's like, why not?
Save the chart, save the world.
Again, let's see if it does. Actually, I did see it's a latency, and it's come back and say that
the
it
latency
does
come
save
back.
the chart.
I don't know, JD. If we keep doing this, they're not going to believe that we can actually do it. All right. Where are we now?
There you go.
We did alerting. Did we do alerting? No, we haven't done alerting.
We haven't done alerting.
All right. So one of the things you might want to do with a query is to set up an alert with it. So JD is going to go to the standard alert creation policy creation, and we're going to add the condition. And here we see an editing window. He's going to give the condition a name. There he is. We see an editing window very similar to the one we saw before, with the little editor thing there. And now we're back in the query notation editor. JD is going to add a query that basically gives the mean utilization of all of the containers by location. And we want to alert if that gets too high. So he's going to put an alert operation there. The alert operation has two arguments. The first is a Boolean expression, in this case just checking a threshold, but it could be arbitrary. And that, when it's true, says the condition exists. And the second argument is a duration that says how long the condition has to exist before we fire an alert. And having set that up, we can now save it, I hope. There it goes. And so there we see it in the alert condition. And the rest of it is the standard thing for just setting up alerts, saying where you want it sent, some documentation. So we're going to go back now to the Metrics Explorer. We saw a join that joined two different metrics. Now we're going to look at a join that takes one table produced by the fetch and the filter in this example. That's one table. And with the squiggly brackets is going to apply 2 continuation queries to that. One that's grouping by the kind of pod the container is in, and the other is grouping everything together and giving the total. We join those 2 and we divide, and that gives you the fraction of core usage time for each kind of pod. And one nice thing you can do with that is to display it with the stacked area graph. And that shows you a very nice breakdown of where the CPU time is going in all of these, in all of your containers. Another thing that is something that you would like to do is to compare things between now and sometime in the past. So here we have a query. Again, we're modifying a table that was produced by a fetch and a filter and also a group by. Is all part of producing a table. This one gives us basically the sum of core usage time for each container name. We do 2 things to it. First, we just add, on one, we just add a time series identifier label that says when is now. And on the second one, we add a label that says when last week. And then we time shift that, the table. And the time shift basically takes one argument that says how far are we shifting. So we're shifting values in the table from a week ago to the present. We're shifting them forward in time. So now we have a table for now and a table for last week that are both at the same time. And you can see the tables here as JD switches between now and last week. You can see the comparison between what was going on last week and next week. Now here we used the union operation rather than the join to combine the multiple tables because we wanted to see both of these independently. Another way to do this is we could do a time shift. And here we are again, time shift. One, we're just changing the name of the value in the table, and the other, we're shifting by a week. And here we do a join and then do a division. And now we see the ratio between what was going on this week and what was going on last week. And some of this looks highly erratic, but that's because this app is being driven by robots, and we keep turning them on and off. So it kind of looks like that. All right, so time shift. Another very nice thing that Stackdriver has is metadata, which describes various aspects of the resources. And here we have the metadata node name for a container. And that basically says what node, what Kubernetes node is that container running on. And so here, we're using that as a filter. We have the name of a node, and we want to get all of the containers whose metadata says I run on that node together. And that's what this filter is doing. And so now we can see for a particular node, what are all the containers that are running on it. So metadata is a very nice thing. It's useful in filters now. It'll be useful before we get into beta in a lot of other kinds of expressions. To group by them or use them in value expressions. All right. And one last thing is, let's see. Oh, no, I got a couple of last things.
Yeah.
OK, so the next thing is, here is a query that basically is got a lot of time series in it. And one thing we might want to do is to sort of cut that down by doing a random selection. And we can do that by using the top table operation with the hash time series identifier operation. So this is now going to pick 10 streams at random by creating a random hash of the time series for each time series identifier for each time series, and then just picking the top 10 of that, which will give us a random selection. You can see as JD moves the cursor and causes the thing to recompute that the selection changes. We could put a seed in here if we wanted to, and then the selection would be stable and would go on. Every time we reevaluate it, we'd get the same thing. Depending on what you want to do, you want one or the other of those. All right, another thing we can do with this, or that we have in the query notation, is macros. And those can be used to kind of structure the way you build a query. So here we've got a macro called container metric name, which takes one container metric, which takes one parameter and fetches a container and a metric name that's constructed from the name, but starts with the Kubernetes container thing. Another macro that does a table operation that just does the filtering that we've seen before. And a third, an expression macro that basically does the regular expression extraction we'd also seen before. And now I can express that query, and we've seen this query before, but I can express it in a much more compact way. And I think at that point, we're ready to go back to the presentation. And all right, I'd say, but wait, there's more. The problem is, I think for most of we've covered most of this stuff now in the demos. Time shifting, alerting, metadata and filter operations. One thing we haven't done is talked about alignment and time. You would have noticed in the group by example where I showed the aggregation computation marching through the time series, that all the time series timestamps lined up very nicely. This typically doesn't happen automatically, or I mean, isn't naturally the case when we're collecting metrics. They tend to be spread out over time. So what has to happen is a kind of alignment operation that takes the time series in a table and lines up the time. Things that need that, like group by and join, need that alignment. We'll do it automatically, but you can also do it explicitly using an align operation. Rate allows you to change from deltas to streams to rates, from things that are absolute changes to changes in time. And every allows you to control the period of evaluation of the queries. All of the queries we've seen up until now have used about a sort of a default 1 minute evaluation period. And actually, there is something I want to show you if we could go back to the demo one more time. Let's go back to the, sorry, JD, I kind of threw it.
What do you want to show?
Put
the macros?
No, well, that's fine. Now you see here that this shows a 1 minute interval, which is the interval of what's showing on the graph. But if we go to a week, for example, we see that the interval, well, you have to get there. We see the interval in the graph is an hour. So each vertical slice of the graph is an hour. Now, we're still executing the query once every minute. And what you see here, in fact, if JD would, if you'll just mouse over the something in the, there we go, you'll see is that there's a central line, which is the average value that we computed over that hour, and then the range of values, 1 minute values we saw in the hour. So you can, as time gets longer and the graph less resolute, we don't lose the spikiness of the underlying data. And we could, if we wanted to, go over to the graph here and add a vertical bar every 1 hour. I'm completely off the script now, so JD's probably going to kill me.
What do you want to do, John?
A line. There should be a line there. No, I'm sorry, every. I apologize. There you go. And then 1H. Yeah, there you go. Now here, we're now calculating the query at 1 hour of intervals, which completely matches the graph, and the shading behind it showing the spikiness has gone away. All right, back to the presentation. And we covered everything else that's on this list. So I think, JD, it's back to you to do a recap. Here you go.
Thank you very much, John. So we showed you a lot of things. There's a lot of information to pack in, and it's a language, and it's hard to digest. Now, the good news is you guys can access this now and play with it. And so if you're a power user, this is precisely the sort of tool that you want to use to get increased observability of your applications, your infrastructure, your cloud services, whether it's Google Cloud or even coming from other cloud providers, cloud-native infrastructure. So every single metric that exists in Stackdriver and the time series, as John mentioned, if they are in our time series database, then we can do all of these things. And so we introduce the Stackdriver Query Notation as a very flexible language to, as John showed, incrementally build and debug, if you want to, very powerful metric queries. Now, you can use it, as we saw, partly with saving the dashboards, but to use it to analyze time series on demand and also to save charts. They are in there. Save charts and to create alerts and so on. Everything programmatically using this query, saving it. There's a ton of other features that the team is planning to bring about. So as, like I said, if you're a power user and this is something that immediately resonates with you, then you're going to use it directly. But we also have a documentation with sort of like a cookbook and examples of things where you can start these basic queries and then extend forward. Now, Stackdriver is just available in alpha. And so you can request access. We have everything here. If this works, if not, use the URL that you see there. It's a closed program that we're running, but please do request access. If you don't get immediately access to it, rest assured, as we expand the program, we'll grant you access. We really want to bring this to all of you and to certainly for the team to get feedback and tell us how we can make it better and most useful to your needs.